Psychology is a science that studies processes within individuals. So the repeated measures design, that is a design that is not just psychological, is perfect for psychology. That is because if we want to investigate processes, psychological processes that happen in our minds, it is better to compare things that happen in ourselves rather than comparing ourselves with other people. So, psychological repeated measures designs are very common in psychology. Repeated measures designs have advantages and disadvantages. So let's start by talking about the work of student or William Gossett and how his first t-test proposed was actually a repeated measures design. So in his paper of 1908, a famous paper that presented the what is now called t-score or t-distribution, but actually Gossett or student used another statistic. So let me tell you the story. In his paper of 1908, he presented this study, in which it's a study by other authors, and there were 10 patients, and a drug was administered to see whether there was an increase in the number of hours of sleep. So there were two versions of these drugs, drug 1 and drug 2, and then that was applied to both drugs, or both versions of the same drug, was applied to each patient twice. Sorry, each one was presented once, was applied once. And then it was measured the number of hours of sleep, or actually the number of additional hours of sleep. So we've got in the first column, for patient 1, there was an additional 0.7 hours of sleep. For patient 2, it was less sleep than the normal, negative 1.6. Same for patient 3, 4, 5. Patient 6 had more sleep, and 7, 8 as well. Patient 9, same amount of sleep, and patient 10 a bit more, 2 hours more, sorry. In drug 2, most of the patients increased the number of hours of sleep, except 1. So the beauty of the repeated measures design is that because these two measures are associated, then we can justify obtaining the difference between these two values. So then in this column we have difference between 2 and 1. And in this case, from 1.9 to 0.7, we've got 1.2. So that's the difference. And we do that for each patient. So we've got 10 new values. And now we can use this variable as a typical variable. So instead of dealing with two variables, like we have to in the between samples t-test or independent samples t-test, here we can use only one variable, the difference between the values of the other two variables. So we've got the values for each of the participants. We've got a mean of 1.58 and the standard deviation of 1.17. So this is not new. Actually, Gossett is citing a previous study. So doing these type of studies wasn't new. What it was new is how to analyze this data. And that's where Gossett provided a distribution. Now, the statistic that Gossett presented in that paper was called Z, not T. And it was actually not the same as the current t-test. So what was the statistic he calculated? Well, the mean of the difference. So if I go back and I show you the mean of the difference scores is 1.58 minus the mean difference of a population. What population are we talking about? Well, remember that populations for this guy, Fisher, are hypothetical. They are a large set of values. So, what characteristics does this set of values have? Well, if you obtain the mean of those values, the mean is 0. Why is 0? Well, because by convention we want to. It's important to compare something to 0. Do we always use 0? No, not always. Sometimes we want to compare to a specific value. It could be any value that we want to compare our sample to. But 0 is a very common. Researchers are interested in comparing to 0 for many reasons. Okay, so basically this would be if the mean of that population is of different scores is 0, then we obtain just the mean difference in our sample. It's the value here in the numerator. What about the denominator? Well, the standard deviation of different scores. And this is the standard deviation of the sample that we have. Okay, so that is the score. And then what he did is to generate a distribution for this score in a population coming. So it's a sampling distribution that comes from a population in which the mean score is 0. So if you create thousands of samples of the same size, and then you calculate this score, the Z score of those samples, then you obtain a distribution of Z scores. And that is the distribution that William Gossett, our student, developed and created. Now, Fisher was much more influential than Gossett. In the book about the research design, he modified the test. He added one component and he called it the t-test. But he attributed it to William Gossett. So that's why we call this the student t. Okay, so what's the difference? Well, he added this component. So the other three components are the same, but in the denominator he divided the standard deviation of the different scores of the sample by the square root of n, and n is the number of observations in the sample. So, and we've got the different scores are 10, so that would be the square root of 10. And then he compares these to sampling distribution of t-scores. So again, there is a slight modification. It followed the idea of Gossett to create a distribution, but it's a slightly different distribution. And the t-distributions have the shape of the distribution varies according to the degrees of freedom. And the degrees of freedom in this case is n-1. Why is n-1? Well, because we are calculating one mean in these different scores, in the 10 different scores. So when we calculate the standard deviation, what we do is to compare values against some values against the mean. And because we calculate the mean, then 9 of those values are free to vary when the mean is fixed, and one of them has to have a specific value, cannot get any value. When you have defined the other 9 values, the other one is not free. You need to have a specific value for obtaining the same mean. So that's why when you calculate a mean, then you need to subtract 1 from the number of observations to obtain the degrees of freedom. Okay, let's go to the example. Okay, so we've got the mean of the different scores is 1.58. The mean of the population is 0 by definition or by convention. The standard deviation of the sample is 1.17, and then the square root of n is 10, so 10. So now we solve for that, and we've got 1.58 divided by 0.323, and that is 4.89. Now, the way of presenting the t-test is t, and between brackets the degrees of freedom equals 4.89. Now, then the t-score is associated with some p-value. And here we've got 2 p-values. One is 0.00043 for one tail, and the other one is 0.00086 for 2 tails.